now we move on to the next talk of this plenary lecture session. Professor Khandker A Muttalib is going to speak now. Professor Khandker A Muttalib was born in Bangladesh, graduated from the University of Dhaka. He did his PhD from Princeton in 1982. Professor Khandker A Muttalib is an APS fellow. His research interests include electron transport as well as energy level distributions in disordered mesoscopic conductors, dynamics of frustrated glassy systems, low energy properties of highly correlated electrons. He was awarded with Joseph Henry Prize Fellowship, Princeton University, Outstanding Achievement Performance Award, Physics Department, University of Florida, Physics Teacher of the Year, and many other awards. Now I invite Professor Dr. Khandker Muttalib to deliver his talk. The title of his talk is Progress in Thermoelectricity, Green Energy for Future. Professor Dr. Khandker A Muttalib.
Thank you so much for your kind introduction. শুভ সন্ধ্যা সবাইকে যারা বাংলাদেশ থেকে যোগ দিয়েছেন.
Thank you.
And good morning to all who have joined from the US. Special thanks to the organizers, Professor Sultana Nahar from the US and Dr. Nazrul Islam Khan from Bangladesh for the opportunity to be part of this US-Bangladesh joint program. Professor Mesbauddin Ahmed was my teacher at Dhaka University. Thank you so much and good to see you, sir.
Thank you.
I am assuming that there are many in the audience, probably most in the audience, who are not familiar with thermoelectricity, and I'm especially aiming to the students and the young researchers. I myself knew nothing about it until I spent a sabbatical at Saclay in France in 2010. And found that my host and friend, Dr. Jean-Louis Pichard, was quite involved in this topic. I was told that the European Union was investing heavily as an alternative source of energy. Now, I knew that thermoelectricity can indeed be a very useful source for green energy, but I always thought that the fundamental principles are all very well established, and any breakthrough, theoretical breakthrough, must come from, or any breakthrough in this area, must come from either experiments or detailed numerical simulations to maybe either find or engineer better thermoelectric materials. And both of these were beyond my own expertise. Nevertheless, I joined many discussions in Jean-Louis' group and eventually realized that although the principles of thermoelectricity itself is indeed very well understood, increasing the efficiency of a thermoelectric device will require more than an understanding of the material properties. It will require novel ideas in the area of nonlinear quantum transport in nanosystems. But let me start with the basics, and I will share the screen if I can. Okay, so let me go to the so I'll go to the slide mode. All right, so can you hear my, can you see my slides, please?
Yes, we can see you.
Okay. So thermoelectricity was discovered exactly 200 years ago in 1821 by the German physicist Seebeck. The phenomenon is very simple. You suppose you hold two ends of some material like bismuth in the form of a wire at two different temperatures. So there's one T hot at the hot temperature, and I will call the other one T cold temperature. And this is my thermoelectric material, which is a bismuth material, let's say. If you hold it at two different temperatures, this material will develop all by itself a voltage difference across this material. So for later references, I will characterize them by their chemical potential. So this is mu C for the cold end, mu H for the hot end. And if this difference in the chemical potentials is large enough, then you can actually connect the two leads and let's say light a bulb. So what you get is electricity from just temperature difference. In other words, what you are doing is you are converting heat energy to electrical energy in a very simple fashion. How does it work? Well, the simple picture is that the hot end typically has a higher density of more energetic electrons. So hot, larger kinetic energy. And so they diffuse from the hot to the cold end until, of course, charge imbalance stops the flow. Now, the actual microscopic picture is slightly more complicated, of course, and needs some special features in the density of states. And therefore, some materials are better than others. So, for example, a bismuth telluride will be a better thermoelectric material in the sense that for the same temperature difference, you will get a larger voltage in this material compared to simple bismuth. So why should you be excited about thermoelectricity? Think about it. About 75% of energy generated by car engine is lost as waste heat, which means that you buy gasoline and put in your car. Only 25% of it is running your engine. The other 75% is completely wasted as heat going to the environment. So now think about it. If you could use your car engine as the hot temperature and the body of the car as the cold temperature, and if you had a thermoelectric material in between, then you could connect it and actually use that waste heat to light bulbs, listen to music, or even recharge your battery. How nice would that be? In fact, heat is a larger fraction of energy is lost as heat in all our power generators. The laptop that you are using to listen to this talk now is getting heated, and there's elaborate mechanism in it to sort of cool it down so that the computer does not overheat. How nice would it be if you actually could use that heat to generate electricity back and run your computer? The advantage of this one is that these systems have absolutely no moving parts and they have no harmful emission. So you get clean energy from waste heat. That's doubly win-win situation. So you might ask, why are we not using it right now? The point is that all these devices that are available currently are terribly inefficient. And by terribly inefficient, I mean that you use this temperature difference, big temperature difference, but you get a tiny voltage out of it. And so in order to light a bulb, you will have to have many of those devices in parallel, and that's not cost effective. They are indeed used. They are used where they are absolutely needed, for example, in spaceships. So in a spaceship, what they do is they use these radioactive materials to provide heat at one end of the material. And of course, the outside temperature is very cold. So there's a big temperature difference. And it's cost effective in the sense that it's much cheaper compared to actually carrying fuel from the Earth to the spaceships. So that's why it's mostly used there. In some cases, you can come up with some very fine-tuned way of having a high efficiency, but they only allow you to have a very low power output. There's this famous example in the mid-90s where there was a proposal from a famous group for a special feature in density of states that creates an efficiency which is the highest. It's the, as big as the Carnot efficiency. But it turned out later on that the power output from that device is exactly zero. So you have a very highly efficient machine which is completely useless. So in this talk, what I will discuss is a proposal for what I call an industrially competitive thermoelectric device, which basically means that it has high efficiency and a large power output, and it uses technology that are already available. Now, I should start with some disclaimers. I mean, what you can realistically expect from this talk. First of all, I'm not an experimentalist like Zahid. If I were, I would have already built the device. I'm also not an expert in numerical simulations, and if I were, then I would probably have used realistic material parameters to simulate a prototype and maybe sell it to a venture capitalist. So what can you really expect from a theoretical physicist like me? Well, what I will do is you will get an explanation of the conceptual basis of the proposed new ideas. What is novel that has been overlooked so far? And an illustration of the opportunities that it offers. Let me see if I can get this one down where, oh, sorry. Okay, I'll just leave it here. So how to use them to design an efficient device. That's part of the thing that you should expect from this talk. So what is new? I will give you some novel ideas that has been overlooked so far. I'll talk about some new experiments that suggest real possibilities and show you some analytic calculations, just the results, not the details, that predict high efficiency and large power output all at the same time. What happened? Okay, so here's the outline of the talk. I'll give you a brief introduction, the efficiency of a thermoelectric device, and all the attempts to improve it. Then I'll basically tell you what has been overlooked so far. And that is related to the novel features in some nonlinear regime that I will tell you in detail. And then I'll give you the proposal. It has two parts. One is how to maximize the number current by using nanowires with some tunable gate voltage. And at the same time, in proposal 2, how to minimize the heat current by using some universality from a theoretical prediction that we have. And in the end, I'll look at the summary and outlook. So here is the linear response regime. What I mean by that is, suppose I have this system, hot temperature, cold temperature, and the thermoelectric material connected to that one. Suppose the difference between that temperature, two temperatures, hot and cold, is delta T, which is very small, suppose. And suppose the resulting voltage difference that I get out of it is also very small, delta mu. If they are indeed very small, then maybe I'll show a little bit of how it appears later on. But then if they are small, then we are in the linear response regime. That is the regime that is theoretically simplest to deal with. And that is the part that we always look at when we look at transport properties. In this regime, the phenomenological efficiency of a thermoelectric device is called a figure of merit. It depends on several material parameters. So it depends on the conductivity. Sigma is the conductivity. Kappa is the thermal conductivity. So in the numerator, you have the charge current. In the denominator, you have the heat current. And it's the ratio multiplied by some Seebeck coefficient, which is also related to the property of the material. What is the energy dependent transmission function of electrons through that one. So the figure of merit or the efficiency depends on these material parameters. So I would like to emphasize that the efficiency in this linear response regime is entirely dependent on the material properties. So if you want to improve the efficiency, you would like to look for good materials. The problem is this Wiedemann-Franz law, which tells you that, well, this is the figure of merit, as I told you in the last slide, T sigma over kappa, this ratio is a fixed constant in metals. It's just a number. There's no way to increase this ratio in a metal. So the figure of merit, if you plug in the realistic values for this Seebeck coefficient, it is always smaller than 1. And any venture capitalist will tell you that, it would be industrially competitive. That means they would like to invest on this one, provided this figure of merit is larger than 3. That is what the typical efficiency that would make it cost effective. So if you want to bring this figure of merit larger than 3, and if this ratio of T sigma over kappa is fixed and S cannot be increased, then the only way you can do better is to beat this Wiedemann-Franz law. Now, this Wiedemann-Franz law is a consequence of Fermi-liquid theory. That's the standard theory, which essentially means that you can, although the electrons are interacting in a metal, you can treat them as effective quasi-particles, not bare electrons, but quasi-particles with some effective mass and some effective scattering parameters. How do you beat that Fermi-liquid theory? Well, you can consider exotic correlated systems in 3D, non-Fermi liquids with highly correlated systems. But those are difficult to produce outside of the laboratory. They typically require very low temperatures and so on. A more robust possibility is to go to reduced dimensions and actually engineer nanomaterials. I see that maybe my this one is blocking the hide names, hide. Okay. So people have tried this. This was proposed. This reduced dimensionality was proposed by Dresselhaus in the mid-80s, and there has been a lot of work along those lines, and we have seen a lot of improvements. But this figure of merit, which is also known as ZT in this community of thermoelectrics, but this figure of merit is always much smaller than 3 so far. So what I'll show you is that there is something very basic that has been overlooked completely. And that is to go beyond this linear response regime where the efficiency depends entirely on material properties. I'll show you that beyond the material properties, you also have another tuning knob that can increase the efficiency for any material, given material. And this, this has to go, you have to go beyond this linear response regime. So let me write down this efficiency in general terms, efficiency, not necessarily in the linear response regime, but in general, is basically the ratio of the number current over the heat current. So this is number current is related to the electrical conductivity. There's the number of electrons that goes to the material. Heat current is the energy that you are putting in. So the ratio is number current divided by the heat current. So you need large number current. That means you need large charge current. And you need a small heat current. So that ratio will give you large efficiency. So let me think about the number current first. So the proposal, part one of the proposal will deal with this number current only, assuming that the heat current is fixed. So the number current is basically an integral over the energy of the transmission function as a function of energy through this material. Multiply this by this function big F of E, which is the difference between the Fermi functions. So remember, the electrons in the hot end is described by its Fermi function Fh with mu h and Th. That's the electrons in the hot end. And the electrons in the cold end has the other Fermi function with chemical potential of the cold end and the temperature at the cold end. So what appears in the number current is this combined difference between the two Fermi functions. If the temperature difference delta T and potential difference delta mu are both small, then what happens is that you are allowed to expand this difference of the Fermi functions in powers of delta T and delta mu. If you keep the linear parts only, then the coefficients are entirely material properties. So that's why the efficiency depends entirely on material properties. What I will show you is that in the nonlinear response case, if you consider this full function, then of course the calculations become more complicated. But now the efficiency, this number current, the eta which is proportional to the number current, and I'll come back to the heat current later on. This efficiency now depends not only on the material properties, but also on the thermodynamic parameters, meaning these temperatures and the chemical potentials of the leads and the load. That is going to be very important. So here is an example. So I have plotted this big F of E, which is the difference between the two Fermi functions in the two ends. It has a negative part, it has a positive part, and it goes to 0 at some particular value, E hat. E is the energy. It goes E hat, where E hat is this combination of the chemical potentials and the temperatures of the two ends. Now the number current, as I showed you before, is an integral over the energy of this, this transmission function, which is entirely material property, and this F of E. So ideally, suppose I give you that this transmission function is some square. Well, it starts at some energy, ends at some energy. If you can manage the E hat in such a way that it exactly coincides with the lower edge, then when you integrate over the energy, you are only integrating over the positive part. However, if this transmission energy starts at some point here, let us say, then when you integrate, you'll integrate over the negative part, you will integrate over the positive part, and they will cancel. So although it is the same transmission function, the same material property, just by tuning this E hat, the thermodynamic part, you can make the number current large or small. So it is this interplay between the material properties, the transmission function, and the thermodynamic properties, the properties of the leads and the loads. it is this interplay that offers a novel opportunity to increase the efficiency. So here is my proposal to take advantage of this interplay. Suppose I have a nanowire, okay? I'll have many of them later on, but suppose I have a single nanowire and one end is at some source of hot temperature, the other end is at some lower temperature, and I have some gate voltage, some possibility of applying a gate voltage in between somewhere. So if it's a nanowire, let's say it's a silicon nanowire, then it has an impurity band, and here is my band, this blue shaded part, and the bottom line, EL0, is the lower edge of this band. And suppose my TH and TC and mu H and mu C are such that my E hat is this red line along this energy axis. So if I can apply the gate voltage to change this lower band edge to this red part, then I'm actually changing my transmission. This electron transmission energy starts from here, ends there. So I'm starting the lower end and mapping it, sort of coinciding it with this E hat by tuning the gate voltage. So what does it do? So here's the calculation. So this, the right-hand panel, so this F of E, this red one, is something that is determined by my TH, TC, mu H, and mu C. And this T of E, that's the transmission function for a disordered nanowire that has been calculated for one-dimensional disordered wire, exactly. So the transmission function starts at EL0. Okay, that's the bottom edge of this band, and ends at some maximum, but this is where E hat is. So if I don't apply any gate voltage, so EL0 remains at this point, then my efficiency, eta over eta C, is the ratio of the efficiency to Carnot efficiency, the highest possible. The efficiency is very small because the material is not very good. Suppose this is my bismuth telluride material. Efficiency is very small, less than 0.1. Now I apply my gate voltage. So what I'm doing is I'm taking this lower edge of the band, applying gate voltage to match it up to E hat. And look at that scale. That means that I need to increase my gate voltage from -2 to -1, so increase the gate voltage by 1 in this unit. So I go from 0 to 1 for this gate voltage, and it goes from almost 0 to almost 0.6 for the ratio eta over eta C. Just because I eliminated the amount of number current which was going in the other direction, in the negative direction, by changing the Fermi function lower edge. So this interplay allows me to increase the efficiency from almost 0 to 0.6. And remember, I said that the figure of merit greater than 3 is the holy grail. In terms of this nonlinear version, eta over eta C, if it is larger than 0.3, then it is considered industrially competitive. So in this calculation, you already reached 0.6 almost. That's what I mean by being industrially competitive. So the summary of this proposal 1 is that take full advantage of the interplay between this microscopic transmission function, which is dictated by the material parameters, and the thermodynamic parameters in the fully nonlinear regime to maximize the number current. And then the way to do it is to have a device with nanowires where you can tune the crossover energy by tuning the gate voltage. Now, one important aspect is that the number crossover energy E hat that I mentioned, that depends on the load, temperature, and also the chemical potentials, This one is actually dependent on the particular load that you put in. So if you are lighting a bulb, the chemical potentials will be something. If you are trying to play a radio or musical instrument, then it will have a different load resistance and a different chemical potential. But by tuning the gate voltage, you can actually tune the efficiency for each different load and each different temperature. And of course, I mentioned that I will have the option of having a large number of parallel wires. So even though the power in each of those nanowires will be small, it is a scalable model so that you can increase the power output simply by increasing the number of nanowires. Of course, there's a limit, but you can do it up to some number where they do not again touch each other, for example. They have to be independent. So that way, this is a scalable thing that you can have a large power output and a large efficiency at the same time. Okay, so that was the part with the number current. What about the heat current? Remember, you need to minimize the heat current. And in general, the thermal conductivity, the heat flow in silicon nanowires is large actually. So that reduces the efficiency significantly. But recent experiments have shown that certain special type of surface roughness can reduce the thermal conductivity significantly. And how do you do it? But, well, before I go to the experiment, let me tell you why this is so important. Because suppose if in order to have less heat current through the system, if I needed to have more bulk disorder that scatters the heat phonons that carry the heat, then I will also decrease the electron current because it will scatter the electrons as well. With surface roughness, with crystalline bulk, you keep the number current the same, so the numerator is the same for the efficiency, but you reduce the thermal conductivity significantly. Problem with this one, this is experimental, and I will show you the experimental plots. Problem with this one is that there's no understanding of these experiments theoretically. There are too many parameters, and if we don't know how to relate those parameters, then there is no way of designing an optimized version of this nanowire. So what we needed is a novel theoretical framework to guide numerical or experimental studies. So here's the experiment. And there are two sets. One is the black, which is, there are two different ways of making this surface disorder. One is by vapor, liquid, solid mechanism. The other one is electroless etching mechanism. And please don't ask me what they mean. I don't know. But apparently they make a huge difference. Look at the electroless etching ELE wires. For the 50 nanometer diameter, so these are the diameters of the wires. For the 50 nanometer, this number is actually so small that it is almost the same as if you had an amorphous silicon. But these are crystalline. But the thermal conductivity can be reduced to the amorphous limit just by surface roughness. So that's very encouraging. And in order to understand the role of this surface roughness, theoretically, we know how to handle bulk disorder. There have been huge amount of work because of electrons propagating in disordered medium, the Anderson transitions, etc. A huge body of work to understand bulk disorder. But what about the surface disorder? Now, there is a proposal from a group, Tosanovich et al. From 1986, who says that, well, there is a way of an exact mapping of a problem of transport in a surface disordered wire and map it to a problem of completely smooth wire, but some kind of a extra interaction in the bulk. That's the pseudo potential. And so for the electrons, the pseudo potential does not have any particular physical meaning. It's just a technical way of incorporating the effect of the surface disorder. We adapted it for the phonons that carries the heat current. And for the phonons, it has a very transparent physical meaning. It means that the pseudo potential is essentially the creation of localized phonons in these wires across the diameter. So once you know that interpretation, then you can come up with a model that you can actually solve. So here's the model that we looked at. It's some Hamiltonian interaction Hamiltonian with propagating phonons and some pseudo potential whose random average should be interpreted as the RMS fluctuations in the surface of the wire. So here is the essential prediction of the calculation with this model. The surface disorder has many parameters in it. So one parameter is the diameter d. One parameter is the roughness, average roughness height, that we'll call it little h. So it's the average height of this corrugation. And there is also a correlation length in any random potential. And the prediction of this calculation, in this theoretical calculation, is first of all that there's a universal t-square dependence, which is not as important for us. But the more important part is that there is a universal disorder dependence. So the thermal conductivity is proportional to the diameter to the some power, correlation length to some other power, and height, this average height, roughness height, to some other power. And the correlation, this thermal conductivity depends on only on this particular ratio, not the independent parameters separately. Because we could not find the exponents directly from calculations, we did some numerical simulations. And indeed, in these numerical simulations, you do see these red parts are actually phonons that are localized. So you do see localized modes of these phonons, and you do see this universal temperature dependence. But more importantly, here is the dependence on the three parameters, D, LC, and H. And you can see this universality coming out, which says that this thermal conductivity is a universal function of a single parameter, zeta, LC to the power half, D to the power half divided by H. So now, when you look at these experiments have different LCs, different H, and different Ds. What you have to now understand theoretically is that no matter what the independent values of LC, H, and D are, as long as you look at this ratio, if the ratio is fixed, the disorder is fixed. You change the ratio and you change the disorder, essentially. So here is the effect of a thermal current, for example, at different surface disorder. So the thermal current has smaller change when you change the disorder parameter. So disorder parameter 45 is basically very little disorder. As you decrease the disorder parameter, you are actually increasing the effect of surface disorder. So this is a model where we look at only effect of a single phonon, okay? One localized phonon. And that changes the scattering by a huge amount as we change the roughness disorder. So this is the effect of, so typically if you have a large number of localized phonons in the system, which is what it should be, a distribution of localized phonons, then this effect would be much larger. This is the phonon frequency. This is 1.5 is our frequency of the localized phonon that we just chose for the calculation. But the effect is clear. So you can then look at this nonlinear thermal conductivity. Okay, so this is the nonlinear thermal conductivity. You can see that it goes from very large one to, as you increase the thermal disorder, you can change the thermal conductivity by a significant amount. And if you have more than one disordered photon, you can go even larger. So the thermal current at different surface disorder, you can calculate that, and that is this effect of a single localized phonon increasing with increasing disorder. Basically, it doesn't matter whether you increase this disorder by changing the diameter, changing the correlation length, or changing the average height, roughness, etc. As long as you have a fixed value of zeta, it will have a fixed value of the thermal current. And so this is the thermal conductivity, and you can see that you can get a sizable decrease with this term. So here's my summary of this proposal for the second part, that the surface roughness for nanowires can reduce thermal conductivity by an order of magnitude without affecting the charge current significantly. And this disorder can be described by a single combination of all these parameters. And so when you are trying to make a disordered wire, if you cannot go to sufficiently small diameter, change the H. If you cannot change H, change LC. So there's a flexibility in designing this one. And of course, this universality allows this flexibility. And it tells us this ELE is satisfies this prediction, which means that it's in this surface dominated wire. So here's my summary of the talk, proposing a thermoelectric device consisting of a series of parallel silicon nanowires with a tunable gate voltage. One can take advantage of an interplay of microscopic and thermodynamic parameters to optimize the efficiency. Power can be scaled up by adding large number of wires. And it has a range of gate voltage where both power and efficiency can be large. And surface roughness is the way to go to prepare this silicon nanowires. And the upshot is that we need more experiments, basically, to see that these effects are useful.
Thank you. Thank you, Professor Khandker A Muttalib. You have finished right on time. It's your time is just over. I would not dare to take questions now. We will let you know if there is any questions. We'll get them through the chat box, and we'll converse. But yeah, this is a great. It's a very interesting topic that you have picked up, and we hope in future we shall have green energy through this method of thermoelectricity generating power.
Need experimentalists like Zahid.
Yeah, we need lots of experiments, and our researchers, students will get inspired to start work on it. Thank you very much for your very interesting talk.
Thank you.
Thank you. We shall now move over to our final talk of the plenary lectures. And this is no other than Professor Eric Cornell.